Example 2. The following table shows the length in meters of the winning long jump in the Olympic Games for the indicated year. So for instance, in 1900, the winning long jump was 7.19 meters. And in 1908, it was 7.48, for instance. Let's find the equation of the regression line that gives the length as a function of time. We'll let t be the number of years since 1900 and L the length of the winning long jump in meters. We'll round the regression parameters to 3 decimal places. So the first thing we're going to do is input our data. To do that, we go to Stat, and we're going to Edit. To clear the data that's already here, we're going to go up to the header, highlight the L2, hit the Clear button, and hit Enter. That clears out L2. We'll do the same thing for L1. Now, in L1, we want to input our variables. In this case, our variable is t, not the year. So t is the number of years since 1900. So in 1900, the number of years since 1900 is 0. So the t that corresponds with year 1900 is 0. The t that corresponds with 1904 is 4, 1908, 8, and 1912, 12. So you want to make sure you input the variable values, not the years in this situation. 0, 4, 8, and 12. The matching function values, that is the length that goes with t equals 0, is 7.19. With t equals 4, it's 7.34, 7.48, and 7.60. Now we're going to plot this data, but first we have to clear out that line that we put in before. So I hit y equals, and I hit clear on y1, getting rid of that line. Now I'm going to plot the data by hitting zoom and then going down to the 9th option, which is zoom stat. Now we have our data graphed. Note, while this data may not be exactly linear, it very much looks like a line would fit quite nicely. So we'll find the equation of that regression line. In order to do that, we go to Stat, over to the right to Calc, and we go down to the 8th option, Linear Regression. We move down to Calculate, hit Enter, and we get the equation of our line. So the initial value is 7.197, and the slope is 0.03425. To write this, our function is L, and our variable is t. So L is a function of t, and our model is linear. So we have our initial value, 7.197, that's rounded to 3 decimal places, plus the slope, which is 0.03, and we want 3 decimal places. So we'll take this 4, it doesn't round up because it's followed by a 2, and then we put our variable, which is not x, but t. So this is the equation of the regression line that gives the length as a function of time. Let's explain in practical terms the meaning of the slope of the regression line. The slope of this regression line is the rate of change of the length per year. So if the slope is 0.034, we're saying that for every year, the length of the winning long jump in the Olympic Games goes up 0.034 meters. So in practical terms, the length of the winning long jump increases by 0.034 meters per year. Let's plot these data points and the regression line. We've already plotted the data points, so let's just add that line of regression. We go to y equals, and we input the line. It's going to be 7.197 plus the slope 0.034 times our variable. In this case, we hit the variable button. It'll put an x even though our variable is t. And we go back to graph. It's already zoomed to our data, so we don't hit zoom. We just go to the graph. And you'll see this line fits the data pretty well. Again, doesn't hit every data point exactly, but it's pretty close. Let's draw this. I'm not done with my graph. I have to make sure I label all the axes. In this case, the variable is t, and that's in years since 1900. And our function is L, which is in meters. I go to the window to see what the bounds are, and I find that the x min over here is negative 1.2. This is 0. The x max is 13.2. The y min here is 7.12. And the y max will go up a little bit, will be 7.7 meters. So my graph has all the data points, the line of regression, both axes labeled with their mins and maxes. Do we expect the regression line to be a good model of the winning length over a long period of time? The answer to that is no. There's a limit to how far someone's able to jump. This model predicts that every year it goes up by 0.034 meters. That's unsustainable. So, no. Because there's a limit how far someone can jump. There were no Olympic Games in 1916 because of World War I, but the winning long jump in the 1920 Olympic Games was 7.15 meters. Compare this with the value that the regression line model gives. Is the result consistent with our previous answer? So this question is asking what is our prediction for the 1920 Olympic Games? That is, what is L of 20? Since 1920 is 20 years after 1900. Our line of regression gives us that this would be 7.197 plus the slope 0.034 times our variable, in this case 20. You can just plug that into your calculator, or since we've already got the formula plugged in, we can go to table settings, plug in 20, go to our table, and the first option should be the value we're looking for, 7.877. Note, 7.877 is much higher than 7.15 meters. So our model gave an overestimate for the winning long jump in 1920. Is this consistent with what we said in the previous part? Yes, we didn't expect the regression line formula to be a good model over a long period of time, since the amount of increase is likely to decrease.